Hey, good morning, students. I guess it could be afternoon or evening, but I'm making this in the morning, and it's a very beautiful snowy day out today. So I'm really excited to study some multiplying polynomials with you guys. So join me for lesson 6 too. So that's exactly what our essential question is how do you multiply polynomials, and what kind of expression is the product. One of the words got cut off there, but what kind of expression is the product? So when we multiply polynomials, you probably think of the most basic multiplying of polynomials we've done, and you might think of the process that we call FOIL. Well, remember that FOIL, the F-O-I-L, is really just the distributive property, but in an organized way. And by the way, I'm very sorry about the background noise, because as usual, I've got a noisy dog here doing something, either snoring or just got done eating, so they're licking their chops, or they're itching, or something. So hopefully it's not too distracting. It is a little bit for me, but hopefully it's not going to bother you too much. So anyway, today we're going to look, remember that FOIL is this organized distributive property, which stands for first, outsides, insides, last. But that is really just the process of distributive property when you have two binomials. Like say you have x plus 2 times x minus 7. But as we continue on to study more sophisticated and high-level math, our polynomials will be much more elaborate. And so we got to go beyond just using FOIL, but the distributive property always works when we're multiplying. When you have two polynomials and you're multiplying, you can multiply any term. So you could take every term in one polynomial and multiply it by every term in the other. Whereas like with adding and subtracting, you can only add and subtract the like terms, but with multiplying, you can multiply anything. So distributive property always works, but I'm going to suggest today another method that I think you might like. You can always continue to use the distributive property. But this seems, as they start to get more elaborate, this method for me just makes me feel a little more secure about my answer and helps me with my organization. And it's called the box method. So I'm going to look at the first few problems of multiplying in both ways. So if I wanted to use the distributive property, the typical distributive property for question A, I would take everything in this first binomial, x plus 2, and I would distribute it. So let's say maybe I take the x and distribute it to each thing in the second one, and then go back and maybe distribute them the 2, right? And so if I distributed the x through to each thing, that would be x times 1, which is x. I'd have x times negative 4x, that's negative 4x squared. I'd have x times positive 2x squared, which is plus 2x cubed. I'd take the 2 now and I'd distribute that. So take the 2, distribute to the 1, and I get 2. I take the 2 and distribute to the negative 4x, I get minus 8x. And the 2 and distribute to the 2x squared, and I get 4x squared. Then I go back through and I put all the like terms together. So I'd start with the highest power, so that's descending order of power. We talked about that's called standard form. So I take the highest power term, and there's just one term with an x cubed, so that's 2x cubed. And I take care of that, and I might cross it off. Then I look at the ones that are squared, so I see that's 4x squared at the end and then minus 4x squared, so those cancel each other out. So no x squared terms. Take the negative 8x and the positive x and put those together. That's negative 7x. Those are done. And finally, the plus 2. And so there were a lot of opportunities there for me to make some errors, mainly because of just organizing. Because, when you get this big long line of terms and you might miss things, so I use strategies like crossing out and using the arrows to make sure I've done all the multiplications. So, but it works, and it's accurate most of the time. I do find I'm a little bit uneasy when I do this. I always look back through the list and just worry that I missed something. And so when I show you this box method, maybe you'll see that you like this better because, again, it's that better organization. So with something like, instead if I did this with the box method, and maybe I'll just do B with the box method instead of having to do A all over again. But with B, instead what you do is you look and see what do you have. You have a 2-term polynomial and a 3-term polynomial. So you make a box, like a little grid, and you can either make it 2 rows and 3 columns or 3 rows and 2 columns. I usually put the smaller polynomial along the side. So basically what I would do is I'd make a 3 by 2 box, and along the side here I'm going to put the binomial 3x minus 4. So I just take any negative signs and just carry it along with the term after it. So that would be a 3x and a negative 4. And then along the top, I just make sure I put it already in standard form. So if it's not already in that descending order, I put it in that descending order. So that would be, the first term would be the negative 7x squared. And then the next one would be the positive x, and then the positive 2. So then how we would multiply is we would just multiply each row and each column together to get a term in each one of these boxes. And then we can go through and look for the like terms. So it's just a little nice organization. So 3x times negative 7x squared is negative 21x cubed. Then I have the 3x. I'm going to multiply it by the next column, which is the x. So 3x times x, that's 3x squared. And then 3x times the 2. So again, what I'm doing here, just to make sure you're following there, I'm just taking this row now with this column. I'm going to fill that in there. So that would be 6x. Then I'm going to go down to the next row, do the exact same thing. So I have the 4 times the negative 7x squared. That's positive 28x squared. The negative 4 and the x is negative 4x. And then the negative 4 and the 2 is negative 8. And then now all I have to do is put my like terms together. Now when you use the box method, what's really cool is as long as your polynomials were in descending order at the start, they will have the like terms on the same diagonal. Now if there's terms that are skipped, like for instance, let's say your first term was an x cubed, but then you went down to an x term for your next term, they might not be, but at least they'll be in the vicinity, not like when you do that distributive property where you could have one x squared term right at the beginning and one way at the end. So the other thing that will be true when you use the box method is that the highest term will be right at the beginning of the box, if you will, and the lowest term or the constant term will be at the end. So you can kind of just write it by looking, starting in the upper left-hand corner and working your way down. So like for instance here, we'd have our highest term, which is the negative 21x cubed. It's right there, right? And then these are like terms right here, and these are the like terms. So these are the x squared terms right next to each other. Add them together. That makes 31x squared. And then 6x and minus 4x is plus 2x, and then minus 8. So would we have gotten the same answer had we distributed? Of course. But again, just the bigger those things get, the more number of terms in each polynomial, the longer that line starts to get if we use straight up distributive property, and the more chances that there are that you're going to miss putting like terms together or miss some multiplications, whereas this way, you've filled in every box, you've distributed and multiplied each term in the first polynomial by the second. So it's just kind of a nice visual checklist and an organizational tool. So on the next two questions, which are the you try questions, I would like to encourage you to at least try one of them using the box method. And just a quick note before you go to try those and pause the video is make sure that you are rewriting, if you're going to use the box method, and really even honestly, if you're not, you should be writing these in standard form. So like for instance with number 3, to start this off, I made a 2 by 3 box, but again you could do a 3 row and 2 column box. This is how I usually do it. I would put 2x here and 3 here. So I'd reverse these so that it's in standard form. And then put the 5x squared here, then negative 7x, because the negative's with the 7x, right? And then the 4 here. So take some time, pause the video, use your preferred method, but at least try one of them, the box method. I find that once people try it at least once, it makes things so much easier. In fact, I was just working with my son yesterday, and he had forgotten that. He's in pre-calculus, and about the box method, and he's like, oh, I forgot. That's so much easier. So give it a try. You might like it. Pause the video now and try number 3 and 4. All right, so thanks for giving those a try. Take a second and check through your answers. Hey, maybe we've converted some people to the box method. Who knows? In fact, my first year teaching honors, well, I guess it was called Accelerated at the time, I had a group of students who just were very passionate about the box method, and they actually made these T-shirts. They had a little club, and I know it sounds kind of nerdy, but they made me a T-shirt too. So someday, maybe when we're in person together, I will wear that. So, so let's continue on. In the next section, we're going to look at modeling with polynomial multiplication. So many real-world situations can be modeled with polynomial functions. Sometimes a situation will arise in which a model is needed that combines two quantities modeled by polynomial functions. In this case, the desired model would be the product of the two known models. Okay. So let's say one is describing like the pricing method of like the pricing for an item, and then another polynomial describes the number of items sold, and if you wanted to know the amount of like the actual potential gross amount of money made off selling them, you would have to multiply those two things for something like that. So anyway, we're going to look at an example where we would have to multiply two polynomials that might not be nearly as pretty as the ones we just did. So, but the key is just being really careful and try to be organized, so the box method helps. So Mr. Silva manages a manufacturing plant from 1990 through 2005. The number of units produced in thousands can be modeled by the function n of x is equal to, and I'll just let you read that on your own. Where x is the number of years since 1990. So that's what x represents here. And the average cost per unit dollars can be modeled by c of x, which equals this function. So we have number and we have the cost, where x is the number of years since 1990. Now, in both cases, the x has to represent the same thing here. Otherwise, we're using the same variable, but for two different things, it wouldn't make sense to combine them. So write a polynomial called t of x, which would be total of x, right? That can be used to model Mr. Silva's total manufacturing cost for those years. So this time we have a cost of items and the number of items that are produced. And so we want the total. So we're going to multiply the two. So if we were going to do that and use the box method, we'd have 3 terms in each. So that'd be a 3 by 3. So we create a 3 by 3 box, maybe like this. And this is going to be kind of a little bit messy. I might have to maybe make a little better box than that. So I promise not to give you too many of these because these are not going to be really all that nice to do. But so this is where box method I definitely think is helpful. And so you want to set this up so that you have one along the side and one along the top. And so I'll put the number along the side and I'll put the cost, but you could do it the other way as well. And then just make sure you carry along those signs with it. So I went ahead and did the calculations ahead of time just to save, but you definitely would want a calculator here. So if you multiply the first row and the first column, so you got the first row, first column, and multiply those two. So negative 0.002x squared times 0.02x squared is negative, see if I can fit that in there, point, and then it looks like, I got it scientific notation on my calculator, but it was 4 zeros and a 4, and then x cubed. That doesn't fit very well in there, so I'll try to rewrite that. So then I do the first row and second column, so now I'm going to do this one right here. So when I multiply those, I get negative 0.002x cubed. Oops, x cubed. Oops, and I just wrote this wrong. This one was supposed to be to the 4th power. Just notice that. Because I wrote this as an x instead of an x squared. Sorry about that. So then, again, first row, 3rd column, and when I multiply those, I get I guess I should be putting a 0 before those. A 0.04 x squared. And now the 2nd row and 1st column, and so that's, let's see, that would be negative 0. And then there's 0.004 x cubed, and then the 0.2x times the negative 0.1x is negative 0.02x squared, and then the 0.2x times the 2 is 0.4x. Yeah, these are not that fun, but definitely make sure you have your calculator. And then now multiplying the final row by the 1st column. So we've got 3 times negative 0.002x squared. So that's a negative 0.006x squared. And then 3 times negative 0.1x is negative 0.3x, and then 3 times 2 is 6. And now to put all the like terms together. So again, the highest term is that first box, and there's no other one, so that would be our first term, so negative 0. And then it looks like there's 4 zeros, 1, 2, 3, 4, 4x to the 4th. And then I'm going to put my like terms together here. So again, I did the calculation already ahead of time, and when I put them together, I got minus 0.0024x cubed. And then I put the next like terms together, so there's 3 x squared terms. When I put those together, I got 0.014x squared. And then when I put the x terms together right here, I got plus 0.1x, and then finally the constant term, which is plus 6. So I know that was not all that fun, but I definitely think it's made easier using the box method. Just gives you a dedicated space for each of those, and being able to find the like terms on the same diagonal really does help increase your likelihood of getting it correct. So with that being said, there is a you-try question. I'm going to let you decide whether you feel like, the process is really the same as when the numbers are easier. It's just, a little harder calculation. So if you would like to give this a try, what I'm going to do is go ahead and put the answer here. So if you want to do it now, pause now and try it, or come back later and try it just to, test your accuracy, I'll give you the answer so that you can check to see if you got it correct. So the correct answer for this should be this whole thing. Couldn't even fit it on one line. Had to go down to the second line. So hope that doesn't discourage you from at least giving it a try, because again, the more practice, it really helps to focus on that the details when you do a problem like this. So kind of like when we did those 3 equation, 3 variable systems. They required a lot of focus, which has more benefits than just getting the correct answer here. It really helps to help with our how long we can maintain focus in a problem. So it challenges your brain a little bit. So let's move on to look at another application of multiplying polynomials. So this is actually my favorite application of multiplying polynomial expressions because it reminds me of doing proofs. And actually, the proofs that you might remember from geometry, maybe don't resemble this, but down the road when you start getting into proving things in higher level math classes, specifically trig proofs, you will appreciate having this opportunity to practice this here. And it's basically, there are these things called polynomial identities. It would be kind of like, like the Pythagorean theorem is like a geometric identity. It's something that's always true. That's what a squared plus b squared equals c squared. Well, these are polynomial identities, so they have to do with polynomials. And then there's trig identities when we study trigonometry. And we, so there are these things that are always true in order to prove that they actually are, so that they become like a theorem, or in this case, an identity. What we do is we would use like the identity and kind of work backwards and say like, okay, well, if we take one side of this identity and we work on it and expand it, or whatever, can we make it look like the other side? So in other words, we try to show that it's true by taking one side that doesn't look like the other side. It doesn't look like these two things should be equal, like in this identity right here. It doesn't look like that x plus a squared minus x minus a squared should equal 4ax. You're like, well, where'd that come from? Where'd the 4ax come from? What we're going to do is we're going to take this left-hand side and we're going to expand it out using our polynomial multiplication. And we're going to show that, in fact, it does boil down to just the same value as just 4 times a and whatever x was. So let's go ahead and do that. So how we're going to do that is by using our distributive property or our FOIL or whatever. So in this case, I'm probably just going to use FOIL. But remember that x plus a squared really means x plus a times x plus a. And then x minus a squared really means x minus a times x minus a. So what we're going to do is we're going to figure out what each of these is, and then we're going to subtract them, and we're going to see if we get 4ax. So the first pair, so that's x plus a times x plus a, first outside, insides last, x times x, that's x squared. The outsides and the insides will both be a times x, so that will be plus 2ax. And then a times a is a squared, so it would be plus a squared. So that's our first quantity. Now the second quantity, when we multiply those out, that would be x squared. And then we have outsides and insides are both minus ax, so that would be minus 2ax. And then negative a times negative a is plus a squared. And now we're going to go ahead and subtract. So remember, when we subtract, it's a good idea to change addition of the opposite. So when you have a whole quantity you're subtracting. So if I change that to plus, everything after it's going to change sign, right? And now I can put my like terms together. So we have x squared and negative x squared. Oh, those cancel out, right? There's no x squareds left. And then 2ax and 2ax is going to make it so we have 4ax. And then we have the a squared and the negative a squared, they cancel out. So see, all that was left when we multiply that all out is 4ax, and that's exactly what we were trying to get it to equal, right? We were trying to get it to equal 4ax, and it did. So that would really constitute what's called an algebraic proof. We showed through algebra that, in fact, this is a true statement all the time. So therefore, x plus a squared minus x plus a squared minus x minus a squared will always equal 4 times ax. Maybe having a specific example would help here. Like, let's say we said x was 8 and a was, I don't know, 3. So that would be like saying 8 plus 3 squared minus 8 minus 3 squared will equal 4 times 8 times 3. Let's see if that's true. So 8 plus 3 is 11. 11 squared is 121. 8 minus 3 is 5. Squared is 25. And 121 minus 25 would equal, I believe, 96. And that's exactly what I get when I multiply 4 times 8 times 3, because 4 times 8 is 32, times 3 is 96. So I just randomly picked an x and an a, and it will always be true that the difference between the sum of those numbers squared and the difference in those numbers squared will always be equal to 4 times the product of those numbers. Now, the importance of that might not be revealed till future and higher level math classes or applications, but this is one of the applications of polynomial identities, or polynomial multiplication, excuse me, is to verify identities. Okay, we'll try one more together, and I'll have you try one for you try, and then we have one more application to look at. I'm going to try to go quickly because I'd like to try to keep this lesson to under 30 minutes, and we're already at about 25 minutes. So in B, we're going to verify this, and again, I'm going to use the box method. It's kind of a little bit tight here, but I think I can fit in, if I write really small here, a box. So this is going to be a binomial times a trinomial. So I've got a and b along the side. I have a squared minus ab and b squared here. And I'm going to multiply and see if it turns out to be a cubed plus b cubed, because they're saying that is the case, that's true. And actually this is going to be a factoring pattern we're going to learn in just a few lessons from now. In fact, that if you have a sum of two perfect cubes, you can factor it in this way. So hopefully you'll remember this when we come back to it. A times a squared is a cubed. A times negative ab is negative a squared b. A times b squared is ab squared. Then take the b and multiply. B times a squared is a squared b. B times negative ab is negative ab squared. And b times b squared is b cubed. Now if you go through and look at your like terms, those are your like terms. So your first term is that a cubed. Okay. And the like terms here on this diagonal, they're opposites, so they cancel out. See how one's a positive, one's a negative? Same thing on the next one. We have a negative ab squared and a positive ab squared. They cancel out. Then all that's left is the plus b cubed. So we were just able to show that in fact that left-hand side equaled the right-hand side. Now we can make a little tweak to this identity, and we would look at another special pattern we're going to learn, which is called the difference of two cubes. And it's, again, going to be a factoring pattern we'll learn down the road. So I'll refer back to this again. I'll say, remember that identity we just proved, and we'll kind of refer to that as we start to factor sum and difference of cubes. Okay, so let's take an opportunity for you to try this. In fact, actually, this right here is that other version, that difference of cubes. So I want you to pause the video now and give these a try, these two a try, and tune back in. I don't really need to give you an answer because you should know what the answer is going to be for each, right? You should be getting whatever's on the one side. So like, for instance, with number 6, if you were to multiply this whole mess here, you should get this. So you'll know, if you don't get that, you did something wrong, right? Because it's an identity. We're telling you it's true. We're just verifying it. It's not like we're proving it for the first time and it may or may not be true. We're saying these are actually true. They're like the theorems you learn in geometry. It's just, can you prove that they're true? So I would definitely use box method on this one. So if you can multiply that binomial times that 5-term polynomial and see if you don't get a to the 5th minus b to the 5th. And then same thing with number 7, show that the left-hand side equals the right-hand side. So pause the video now and give these two a try. All right, so thanks for giving those a try. And in each case, you were able to verify that the big, long, messy polynomial multiplication actually did equal the much simpler other side of the identity. So in the first case, a to the 5th minus b to the 5th, and in the second one, a to the 3rd minus b to the 3rd. And in fact, these identities do hold the key to factoring higher degree polynomials. And we've done a lot of factoring with quadratics. We've even done some 4-term polynomials, like with the factor by grouping. But to factor even more elaborate polynomials, you need to know that these patterns are true so that you can use them to break down these higher degree polynomials. So Anyway, thanks for giving those a try. And you could specifically plug in numbers here if you wanted to show that. Like, say you picked a number for A and B, you could substitute in everywhere you say A and B, and you could, verify. You could show that, in fact, you get the same numeric value doing both calculations. The much easier one with the two terms, right, and then the one with the more elaborate binomials and whatever, 5-term polynomials. So, final thing. And this one I would say is a little bit of a reach, but nonetheless, we'll still talk about it. And that's using polynomial identities for simplifying algebraic expressions. So it says the most obvious use for polynomial identities is simplifying algebraic expressions, but polynomial identities turn out to have non-intuitive uses as well. In my mind, when I see non-intuitive, that just means like things that you wouldn't necessarily think of, and there's probably a reason why we don't think of them, and that's because we have calculators these days for this particular situation. But we're going to use like these little identities to do some calculations where we could just do it with a calculator or other methods. So that first one though is about Pythagorean identities, or Pythagorean triples, excuse me. So you may remember a Pythagorean triple is a set of 3 integer values that make a right triangle. So the most common one is the 3, 4, 5 right triangle. That just means it's a right triangle where the two legs are 3 and 4 and the hypotenuse is 5. Now, most of the time, the 3 sides of a right triangle are not going to all be integers, right? So when they are, they have a special name called a Pythagorean triple. So you could use this identity, this x squared plus y squared squared equals x squared minus y squared squared plus 2xy squared to identify a Pythagorean triple. Using, just say you could pick 4 and 3. So let's say we know the 2 of the legs of a Pythagorean triple are 3 and 4, and we wanted to use that to produce maybe another Pythagorean triple, say like another set of 3 numbers that are all integers that make a right triangle. So what we would do is we would take that x of 4 and plug that in wherever we see x, and the 3 for y, and again in every situation we would just plug that in, plug the x in for x and the y in for y, right? And when we do, it would look like this, right here. Right there. And if we simplified that, what it would do is reveal another Pythagorean triple. So 4 squared plus 3 squared. Well, 4 squared is 16, 3 squared is 9. If you add those together, that's 25. So it would say 25 squared is equal to, well, 4 squared minus 3 squared, that would be 16 minus 9, which is 7. And then plus 2 times 4 times 3, so that would be 2 times 12, which is 24. And basically what it just revealed now is that another Pythagorean triple would be these 3 numbers, 7, 24, and 25, with 25 being the hypotenuse. So the legs would be 7 and 24. The hypotenuse would be 25. Now here's another one you could do. So let's say we wanted to use another Pythagorean triple that I happen to know is 6, 8, 10. And the only reason I know that is I'm just doubling the 3, 4, 5. So let's say I use 6 and the 8, right? And then, of course, the other one is 10, but I'll just use the 2 legs, basically. And if I plug these in here, it would be 6 squared. Oops, actually put the bigger one first. 8 squared plus 6 squared squared equals 8 squared minus 6 squared squared plus 2 times 8 times 6 squared. So again, this is going to produce another Pythagorean triple. So 8 squared plus 6 squared squared. So 8 squared is 64. 6 squared is 36. Add those together, you get 100 squared. And then 8 squared minus 6 squared, that would be 64 minus 36, which is 64 minus 36 is, I believe, 28. And then 2 times 8 times 6 would be 2 times 48, which is 96. And what that's showing there is that if you had legs of 28 and 96, then the hypotenuse would be 100. And that's another Pythagorean triple. A very large one, but still another Pythagorean triple. So 28, 96, and 100 would also make a right triangle, with 28 and 96 being the legs. We'll wrap it up with this last one, and if you'd like to try the you-try questions, I will put the answers, or well, maybe we'll just skip the you-try questions on this. The lesson's already getting pretty long. So with this particular one, this identity is sometimes used to square numbers. Now, why we would not just multiply the two numbers using, like, manual multiplication or use a calculator, well, that's for you to answer, I guess. But if we wanted to use this identity, let's say we wanted to square 27. So if we think about two numbers that would make 27 that are really easy to square, we may think of 20 and 7. So if we could rewrite it so that x was 20 and y was 7, then we could use this method to square 27. We could take the x plus y squared, so that would be 20 plus 7 squared is equal to x squared, which would be 20 squared, plus 2 times 20 times 7, and then plus 7 squared. So we split it up. Instead of doing 27 squared, we do 20 squared plus 2 times 20 times 7 plus 7 squared. So we just take the two pieces that made the sum of 27 and we use this identity. So that 20 squared would be 400. 2 times 20 times 7, that would be, let's see, 40 times 7, that's 280. And then 7 squared is 49. And then add those together, and that adds up to, I think, 729 when I add those up. And 729 is the answer. Yep, which is what we'd get if we took 27 and we squared it. Which I guess you could have done it just using plain multiplication, right? But again, I know it's a little bit of a reach, but it is an application of one of these identities. So we'll go ahead and wrap it up. If you do want to try the you-tries, I'll just write down the work that I have. Actually, I'll take a picture of the work that I have for these and post this here. So if you want to give them a try, just to get a little practice, you can. If not, I'm sure there'll be some included in the homework. So here are the answers. And number 8 is 1591, and number 9 is 324. So again, if you want to give those a try, take a look back once you've tried them and see if they match up with the answers that you see here. So thanks for hanging in with me today, and I'll see you in class.